Hello, everybody. We will start the session with a preview of ISSTA 2021, which will be given by Kristi Kadar, who will be the General Chair of ISSTA 2021, and Zhangyu Zhang, who will be the Program Chair for the conference. And you can post questions on Slack under day 30900 Keynote 3 channel. Kristi, you can share your slides and please, you have the floor. Thank you.
All right, thank you, Corina. So ISSTA 2020 is not over yet, but my job here is to get excited about ISSTA 2021 already. So I'm the General Chair for ISSTA 2021, and I'm joined by Zhangyu Zhang, who's a Program Chair for the conference. So before I give a preview of ISSTA 2021, let me offer big thanks to Corina and Sarfraz and the entire ISSTA 2020 organizing team for a great conference under difficult and unpredictable circumstances. So I know that as early as a couple of months back, right, we're still hoping to see each other in person in LA, but in the end, it turned out quite nicely online as well. And this being said, I do hope to be able to see everyone next year at ISSTA 2021, which will take place in Aarhus, Denmark, between 12th and 16th of July 2021. And next year, ISSTA will be co-located with ICOOP after another successful co-location in 2018 in Amsterdam. So we're looking forward to that. So where is Aarhus? Well, it's in Denmark, in Northern Europe. You have a map of Europe here, with Denmark highlighted with the flag of the country. And Aarhus itself is on the east coast of the main Jutland Peninsula of Denmark. It is Denmark's second largest city. It's quite a lively city with a mix of old and modern buildings, beautiful parks and beaches, and interesting museums. So I think a place that I'm looking forward to hosting ISSTA. Aarhus, well, the conference itself will be hosted at Aarhus University, which is the largest and second oldest university in Denmark. And I also noticed that it's often the campus of Aarhus University. It's often voted as one of the most beautiful in Europe. So very nice place to host the conference. And here I also want to offer big thanks to Anders Möller, who's a professor at Aarhus University and the general chair for ICOOP 2021, and also an active member of the ISSTA community for hosting us there. Oops. All right. So next year we will also be celebrating 30 editions of ISSTA. Incredible how time flies. I remember when ISSTA was supposed to be a new conference or one of the newer conferences. So we are now quite old. So we are looking at organizing a special celebratory event there. So I'm just one of the people involved in the organization. And of course, the conference will not be possible without an excellent organizing committee. And here it is. So Zhangyu Zhang is the program chair, as I mentioned. The workshops will be organized by Marcel Böhme and Maria Christakis. The doctoral symposium by Eric Boden and Wei Le. We'll have a tool demonstrations track, as always, organized by Michael Pradel and Mike Papadakis. An artifact evaluation process run by Manel Rieger and Martin Novak. We also have a summer school running in parallel with ISSTA, organized by Frank Tiep and Andreas Zeller. The sponsorship will be run by Darko Marinov and Omar Tripp. We'll have a poster session run by Ajita Rajan and Sebastian Edveg. Our publicity is run by Lisa Nguyen Quang Do, and our web presence by Daniel Grunberg. So I'm looking forward again to a great conference next year as well. And now I'm going to pass it to Shang Yu, who's going to tell you a bit more about the program, call for paper, and upcoming deadlines. So Shang Yu, I think you can share the screen.
Thank you, Christian. Let me share screen. Hello, everyone. This is Xiang Yu. I will be the program chair for next ISSTA. In the next few minutes, I will talk about the planning of the main program. Next year, we call for 3 kinds of papers: technical papers, experience papers, and reproducibility studies. An experience paper talk about experience of applying testing and analysis technique in practice. And reproducibility studies talk about those that we try to reproduce some of the paper that were published in the past. And this paper may use proprietary data and may be difficult to reproduce. And the paper review will be double blind, like in the past few years. And each paper will have 3 reviews. In some needed cases, we're going to assign additional review. And the author will have the opportunity to respond to all the reviews. So, and these are the important days. The paper submission deadline will be January 27th, which is a Friday. And then the response period will be March 24 to 27. And the notification will be April 19th. These days actually are similar to the deadlines in this year. And the program committee, we actually have finalized the PC. We have 45 PC members, 2 more than this year. And we have a pretty good coverage on the areas, especially on the growing areas, such as deep learning, system testing, analysis, data analytics in software engineering, CPS system testing, analysis, fuzzing, and so on. And many of you actually may be curious about the form of the conference. What we can say at this moment is that we are closely monitoring the development of the pandemic situation. We hope we're going to have a physical conference. Of course, in the meantime, we also have a backup plan for the virtual conference. And nonetheless, even if we're going to have a virtual conference, we understand many of you may have the visa restriction or the pandemic-related issues and may not be able to travel to the conference physically. So we plan to provide a streaming alternative for those that cannot travel. So at the end, I want to encourage you to submit your great work to ISSTA next year, not only to the main conference, but also to the other tracks, such as Artifact, 2Demo, Doctoral Symposium, Poster, and the workshops. And please consider attending the summer school. I look forward to a successful ISSTA 2021 and look forward to meeting you there. Thank you.
Great, thank you both. We don't have questions, so all I can say is that we are looking forward to a successful event next year, hopefully in person. So we'll play it by the year, I guess, but hopefully things will improve. And nice to see you both, and I hope you'll enjoy the rest of ISSTA 2020.
Thank you, Corina, we will.
Thank you. So we will take a short break and we will resume at 9:30 for the 3rd keynote of ISSTA 2020, which will be given jointly by Gordon Fraser and Andreas Zeller on the occasion of receiving the ISSTA 2020 Impact Paper Award. Gordon Fraser is a professor at the University of Passau in Germany. He received his PhD from Graz University of Technology in Austria. He worked as a postdoctoral researcher at Saarland University in Germany with Andreas. And prior to joining Passau, he was senior lecturer at Sheffield University in UK. He has published extensively on improving software quality and programmer productivity at all major software engineering venues. He also chairs several important testing conferences. He is a founder and a core developer of the well-known Evo Suite tool. He received award funding from Microsoft and Facebook. And besides being a computer scientist, he's a classical pianist and a former village organist. Andreas Zeller is faculty at the ISSTA Helmholtz Center for Information Security and also a professor of software engineering at Saarland University in Saarbrücken, Germany. His research on automated debugging, mining software repositories, specification mining, also security testing has been highly influential. He is an ACM fellow and also holds an ACM SIGSoft Outstanding Research Award. The ISSTA 2020 Impact Paper Award was given to their ISSTA 2010 paper on mutation-driven generation of unit tests and oracles. And this paper had a lasting influence on the research and practice of software testing and analysis. It received more than 150 citations for the conference version and more than 370 for the journal version. Congratulations again for this award, and the floor is yours.
Okay. Can you see my screen?
Yes.
Okay. So thank you very much. I'm very humbled to receive this award. So really, thank you very much. We'll split this talk in two. So I'm going to start. Andreas is going to follow up. I'm going to provide a bit of a historical perspective on what we did and what has happened in the 10 years since the paper was originally published. And then Andreas will give a bit of a more visionary outlook, I suppose. So the background of this work was, at the time, I was a postdoc at Saarland University, and Andreas's group is a picture of us in 2010. And at the time, Andreas was fascinated and working on the topic of testing. And if Andreas is enthusiastic about a topic and you're somewhere close to Andreas, if you know Andreas, you'll know that it's very difficult not to also become enthusiastic about whatever topic Andreas is enthusiastic about. So at the time, one of the topics he was enthusiastic about was testing, in particular mutation testing. So part of the work happening at his group at the time was work on the Javalanche mutation testing system, which is a Java bytecode mutation tool. It's supposed to be very scalable, well engineered, and it integrates DICOM in order to estimate how likely mutants are to be equivalent. So it targets one of the most challenging problems in mutation testing. So this is the work environment I came to join as a postdoc. And so I got to work with some awesome tools there, one of them being Javalanche. Javalanche uses Mike Ernst's DICOM tool in order to infer invariance, which Javalanche uses to determine which mutants are likely to be equivalent. Some other tools that were around at the time and offered themselves to play around with. Also, Mike Ernst and his colleagues' Randu test generator. Randu is a random test generator using feedback-driven random test generation for Java code. And you give it a set of classes, methods you want to test, and it exercises them randomly in order to find violations of contracts, for example. And the fourth tool I'd like to give credit to is Paolo Tonella's eTalk, which was also roughly around that time. And it's a search-based tool which aims to generate unit test cases for Java classes, which is supposed to achieve code coverage. So if you take these four tools, Java Launch, Daikon, Random, and eTalk, and you combine them, then essentially what you get is a tool which we called MuTest. And MuTest is what the 2010 paper at ISSTA was about. So ISSTA 2010 in Trento, I found the old slides, and I'm going to give you a cut down version of the presentation from 2010. So no worries, I'm not going to go through the entire presentation, but two things you might notice here. First, affiliation's different, and second, the trendy style was the Steve Jobs iPhone presentation style in Keynote. So the motivation for the work at the time was we want to generate unit tests. A unit test looks like this. It's nice and short. It focuses on a single class and maybe methods in that class. And besides exercising the class in a particular way, it also contains assertions that check the behavior of the code we have exercised. And the main paradigms used to create these tests are primarily manually. So you write the tests, and you pick some scenario you want to write your test for, and then you also have to consider which assertions should be contained in that test case. So at the time, there was plenty of work happening in the area of generating tests. And the main idea behind this was that to reduce the effort of developers, if we can automate either of these two bits, writing the tests, writing assertions, that's going to help developers. And so the main focus at the time was on generating these tests with the assumption that once we've produced the inputs, this is going to be helpful to developers, and they can then write the assertions and provide the test oracles. A third perspective popular at the time was parameterized unit tests. The PEX tool was just popular, starting to become popular at the time. We write a somewhat more abstract parameterized test case with its assertions and then automatically generate some values that exercise the code described by the parameterized test. So in these available choices of how you can try to come up with your test cases, we identified the following issues. The first one is that if we take existing methods to generate these tests, then this is going to be either randomly or targeting coverage criteria. But we're not really satisfied with covering code. What we want to do is we want to have tests that actually help us reveal faults. And the second issue in these available approaches is that the one step that is not automated at any point here is the part of writing assertions, creating the test oracles for the tests. So we're facing the problem of how can we generate or how can we create test oracles? In principle, creating test oracles is another search problem. We can, Daikon style, generate any number of possible assertions for any given sequence of calls. And so this means that we somehow have to identify, given a large number of possible assertions we could generate for a test at hand, how can we know which of all these possible test oracles are those that are effective at finding faults? So this is what the MuTest approach does. It takes a Java class under test, then it creates mutants, which are artificial defects where we replace operators, method calls, statements, and so on. And then MuTest will take a mutant at a time, generate a set of calls on the class under test that will exercise that mutant, and then it will add an assertion such that if you execute the test, the assertion will be able to distinguish whether it was executed on the original version of the class or on the mutated version. So there are two problems here. How do we generate these sequences, and how do we generate these assertions? To solve the first of the two problems, generating the sequences of calls, we resorted to search-based testing. So we cast the problem of creating test cases as a problem of optimizing sequences of calls. Once we've cast it as a search problem, we can use any available efficient meteoristic search algorithm in order to optimize solutions. So we had to come up with some kind of representation that allows us to convert this to a search problem. And in our case, the representation is a sequence of calls. You'd have a sequence with calls to constructors for a class under test, calls to methods in that class, and the sequence can have any length and it can vary throughout the search. Once you've defined a representation, then the search algorithm will typically produce a whole population of these candidate solutions, usually randomly, and then different search operators are applied. So we might mutate individual calls by replacing methods, by replacing parameters, and so on. And there's crossover where we cut sequences apart and stitch them together differently. And all this is integrated in the general framework of using genetic algorithms. Now, the other component we need in order to apply a search algorithm, like a genetic algorithm, is an optimization function. And that optimization function needs to guide the search towards achieving the goal. Our goal is to generate sequences of calls that will help us to identify mutants. So what MuTest used was a combination of 3 metrics. The approach level and the branch distance are very traditional search-based testing metrics. And in 2010, the day before I gave this talk in 2010, much younger Phil McMinn actually gave a tutorial on search-based testing. So everyone in the audience probably knew exactly what branch distance and approach level are at the time. What we had to add on top of this was what I call necessity conditions. So it's not sufficient to execute faulty code. You need to execute it in a particular way such that it infects the state and thus leads the execution to some observable difference. So we had to come up with something to use as an optimization function for this necessity condition. And we took inspiration from Javalanche for this. So what we did was we execute a test case on the original program, and we execute the same test case on a mutant. We observe the execution traces produced by these different, by the same test on these different versions of the program. And the more these 2 executions differ, the more likely it is that there is something different in the execution that we're going to be able to observe. The more damage the mutation does, the easier it will be to observe it. And so we want to maximize the amount of damage the mutant does during the execution such that it becomes easier to then add a test oracle that identifies the mutant. So the fitness function we used was essentially the sum of functions in which the coverage changed. And the idea behind this is if we maximize the impact of a mutant, then it's going to be easier to observe this. So this is the first part, the search in order to generate the sequences that reach a mutant, that execute the mutant in such a way that it has an impact on the execution. The remaining part is, after we have generated these sequences, is to generate assertions for these sequences. In order to solve this problem, we used an approach similar to what essentially Daikon does. You execute the test case on your program, and during that execution, you can make observations at any point in the execution. So after each of the statements in our execution, we observe the state, for example, by calling observer or inspector methods on the objects we've created. And an inspector method would be a pure method, no side effects, that has no parameters and returns a primitive value, is empty, for example. And if you execute your test case and make these observations, then you'll create a trace of different things that you can observe, different inspector results. And if you execute the same test on a mutant and perform the same observations, then possibly some of these observations may differ if the mutant had an effect on the execution. So in our example, inspector 1 differs on the mutant execution from the result we retrieved during the regular execution. And so this is what we want to focus on when we generate assertions. If we want to generate an assertion for this particular test case, at this point, we would add an assertion that checks the content of this particular inspector. So for example, and at the time I used JODA-time source code for examples, an assertion could look like this, where you call an inspector function, get millis, we get milliseconds, and we take the observed value from the value returned by the regular execution. So essentially the test cases are regression test cases that capture what the program is currently doing. Now, the inspector traces is like one possible thing you can observe, and there's many different other things you can observe. For example, in a typical test case, you'll have different objects that you can compare with each other. So you can do all pairwise combinations, and then if two objects are equal on the regular execution, but they differ on the mutant execution or vice versa, then that suggests that this would be a good place to add an equals assertion that compares these two objects. So with this, we get for each mutant one or more assertions that check the state after the execution. But we have many mutants. We don't just have one mutant, but for each test case, we potentially cover and execute several mutants. And for each of these mutants, we can get different assertions. So really what we've done at this point is that we've narrowed down our search from this very large set of possible assertions to a subset of these assertions that are actually potentially relevant, but there's still some redundancy in there. But at this point, it's a simple optimization problem of selecting a subset of sufficient assertions in order to detect all the mutants that the test case can detect. So this, in a nutshell, is what MuTest does. In the initial paper, we evaluated it on 2 Java libraries that are quite well known at this point, Jolatime and Apache Commons Maths. They have been both used in many different papers and are also part of Defects4J and other bug databases. So we picked all the public classes from these 2 projects, and then we compared the human written tests with the generated tests, and we compared things like the performance at detecting the mutants. And then, as you can see in this diagram, the test generated will be more effective at detecting these mutants. So essentially, MuTest test suites find significantly more seeded defects than handwritten test suites. In the original presentation, there's loads of other statistics on the size of test cases and a number of assertions, and I'm going to skip that. And I think at this point, you have an overview of what the original work was about. And in the 10 years since that conference, after producing a journal extension, I think that was the last ISSTA where there were special issues with invited papers. Google Scholar tells us we have roughly 370 citations, and some of the papers among these 370 are inspired to address the same problem, that of generating tests from mutants and generating test oracles. Just picking some examples, there's work on mutation testing for high-order mutants by Mark Harmon's group and C programs, or work from Ali Mesbah's group on using similar techniques to generate oracles for JavaScript code. But rather than surveying all the 370 papers, I would just like to pick out a couple of things to point out. So there are some papers in these 370 that generally just took inspiration by the idea of using mutation as a tool to identify relevant aspects of software and faults, such as papers on mutation-based fault localization. But there are 3 central problems that we addressed with MuTest. One is mutation testing, then there's the problem of generating test cases, and the oracle problem. And what I'd like to do is, for the 2 problems of test generation and the oracle problem, I'd like to pick for each of these my favorite follow-up paper that has followed from the original MuTest work and highlight why I like that. Before I do that, maybe there's one thing I need to point out, and that's, you might have asked yourself the question, where is MuTest? Don't think anyone has ever seen MuTest since then. The reason for that is that at the very same conference where this was presented, my good friend Andreas was also there, and we discussed a particular problem, the downside of this particular approach at this conference. And so the problem is that while MuTest was efficient at generating tests for individual mutants, typically we have loads of mutants. And then things don't scale so well as soon as you have large numbers of test objectives that you need to address, like large numbers of mutants as you traditionally get. So what happened was we came up with a better representation as a search problem We took inspiration from MuTest's source code, but essentially rewrote it, and the result is EvoSuite. So to the present day, the assertions that EvoSuite generates are generated exactly using the approach described in the MuTest paper. And if you run EvoSuite using the criterion of strong mutation, then it's going to use exactly what MuTest did. But it has also evolved and covers other things. Like, for example, we're not only targeting mutants, but we're also looking at coverage criteria, computational complexity reasons. But if you want to try out MuTest, essentially what you have to do is use EvoSuite and run it with strong mutation testing. In terms of follow-up, I just wanted to show one nice picture which came from applying this idea of evolving test suites rather than test cases. Here's Mark Harmon's group looking very chuffed after their Sapiens test generation tool was acquired by Facebook. Sapiens implements this whole test suite generation approach that I just described. Okay, but what I'd like to point out with respect to follow-up work on test generation is this. When we selected a genetic algorithm in MuTest, we used this because we didn't really understand the problem very well, and it wasn't clear what algorithm would be suitable to solve that problem. This is a scenario where a genetic algorithm is very well suited. And the same genetic algorithm, essentially, it's also what is used in EvoSuite, just the representation has changed. And so essentially, the search algorithm for us is a black box. We know it produces something, and we're happy with the result, but exactly when it works well and when it doesn't work well is very difficult to judge with the black box. And these black boxes are actually quite common in the research we're doing. For example, if you change a couple of things in this setup of what is evolved, if you use the test to calculate the fitness function and then the result of the mutants, then what you're looking at is program repair. And again, you have a black box that does the search, which could be the very same search algorithm as we use for test generation. And these days, many other different black boxes are used in our day-to-day software engineering research. And so I'd like to highlight 3 very simple experimental things that we can do on a search algorithm in order to shed light on what the search algorithm does internally. And I'd like to say why that is important to do. The first thing is a thing you should always do if you use a search algorithm, which is compare how your search algorithm performs with the baseline of a random search. So what this diagram shows us on the y-axis is the success rate on different coverage goals of a random search. And on the y-axis, we have the success rate for the same goals on a search algorithm, a genetic algorithm, using the guidance I described. So we can split this diagram into 4 parts, and then we see different behaviors in these 4 parts. And so up here, I labeled easy goals. These are coverage goals which are easy to cover by a random search, but they're also easily covered by the search. And these are probably trivially easy classes, Java beans maybe. Then we have a couple of dots in this corner down here. These are classes or coverage goals that were covered by an automated, by the random test generator, but not by the search. Something must be wrong here. These are likely bugs in the search algorithm. Down here, we see actually a substantial amount of them, hard goals. These are coverage goals that the test generator just generally failed to cover. If you're looking for a research problem and you want to contribute to test generation, all you need to do is pick anything in here, and it's going to be a problem that we haven't solved yet. And then up here, we see parts where the coverage goals where the search actually works very well. And by doing this simple comparison, we can now have a look, what are the different aspects of cases where it does work very well, and what are how do they differ from cases where it doesn't work very well? Simple thing to do would be looking at the number of method executions since we're generating unit tests, okay? So for the easy goals, which are up here, we can see that the average number of executions during a regular search execution is significantly higher than in any of the other quartiles of our diagram. And as you'd expect, we hardly manage to even execute the methods in the hard goals. This is likely because the test generator struggled to instantiate relevant objects, or because there is some implicit preconditions which it just didn't manage to satisfy. We can use other metrics to validate that hypothesis. For example, if we look at the number of exceptions thrown during execution of the tests, we'll see that for all these cases that are in our hard category, we get substantially more exceptions thrown. And this just indicates that the test generator really struggled in order to generate valid instances and valid calls. Another thing we could look at would be the difference in fitness values we observed. So what this diagram shows us is the total number of unique fitness values seen on average during execution. Well, the cases in our top left quartile, where we have the search performing better than random search, we see that the distinct number of fitness values is substantially higher than in all the other cases. And this leads me to the second simple thing we can easily try if you have a black box and you want to understand it better, which is fitness landscape analysis. So, simple concept, this diagram plots the fitness landscape for a given search problem. This means on one axis we've got the input values, so it's a simple problem with a simple number we're trying to optimize, and our y-axis is the fitness value allocated to each of these points in our search space. Right, so we have a global optimum up here, and if we start our search algorithm anywhere, it'll have a nice gradient to climb and find our search objective. Search landscapes rarely look like this. In practice, you typically have things like local optima, where your search can get stuck. There are well-known techniques to overcome this. The genetic algorithm is quite well suited to do this. We might not have one local optimum, we might have loads and have a very rugged landscape, which makes it more difficult to do the search. But then we might also have the opposite. We might have a very flat landscape, which is also very difficult, because if you try and do search anywhere along such a plateau, all of the neighboring values have the same fitness value and the search algorithm doesn't know what to do. And the worst case probably is this kind of fitness landscape, a needle in a haystack, where everything has the same fitness value except for the thing you're looking for. And then of course there's no guidance. So a simple thing you can do to identify what sort of problem you're facing is this. You do a random walk in your landscape. You pick a random point and then you mutate it a couple of times. That gives you a couple of fitness values, and you can use the trace of fitness values to determine what type of fitness landscape you're facing. Okay, so a simple metric we typically use in fitness landscape analysis is the autocorrelation. Essentially, you take the sequence of fitness values and then you correlate it with the sequence off by an offset. And if the correlation is very high, then that suggests that not a lot is happening and you've got a very smooth landscape. If we look at the problem of test generation, then the autocorrelation is super high, which means it's actually very, very smooth. Is it very smooth because there's nice gradients? Unlikely. And there's other metrics you can apply to your random walk to determine this. For example, we can look at the neutrality distance, which is the number or percentage of steps in random walks that you have to take before you encounter a different fitness value. Right? So this means that roughly 20% of the steps in a random walk had to be taken before, on average, we observed a new fitness value. So from observing these things, we can really conclude our search landscape looks roughly like this. Maybe it's not quite that bad. Maybe we have a couple of plateaus in between, but it is pretty bad. And we also know that this isn't always the case. For some search problems, we see that the search performs much better and the fitness landscape is more is better suited for them, right? So we see a strong correlation between some of these metrics and the fitness landscape. The higher the neutrality distance, the lower the success rate of our search algorithm. Okay, so fitness landscape analysis was the second of the three techniques I just wanted to briefly point out. And the third one is to simply look at what is happening inside the population of the algorithm while it is evolving. So this plot shows 4 different groups of classes which were identified in a set of experiments, and it shows how coverage evolves over time. So this is the type of diagram you'd see in a paper, which shows how well the algorithm works. So we've got one case where essentially nothing happens. The algorithm has achieved some coverage initially, but then no evolution happened. There is the red line where the coverage keeps growing even right up to the end, and so probably if we continue the search, the coverage would increase. This turquoise line here has some growth initially, but then flattens out and the search is stuck. And for the purple line, it keeps increasing until right before the 10 minutes, but then it kind of converges. So if we want to understand how these classes differ, what we can do is we can look at the internal dynamics within this population. We can look at things like, for example, how does the size evolve? If you remember, the length of the individuals we use is part of what the algorithm itself determines. And so what happens is that typically the population grows vastly immediately, and then after a minute, it shrinks. But for some cases, it doesn't shrink quite so much. And these are the cases where the search is stuck. Or we could look at the entropy. So the second diagram here shows us the relative entropy compared to the initial population. And in those cases where the search is still busy evolving, we see very high entropy relative to the initial entropy. Whereas for the cases where it's stuck, there's absolutely no entropy left. So these are three examples of things you can do in order to understand your black box. And if you truly understand what happens in your black box, then that you can use in order to come up with a better suited algorithm that better solves the problem at hand than the generic black box. And so the first of the two papers I want to point out is emerging from the ideas initially proposed in the ISSTA 2010 paper is reformulating branch coverage as a many objective optimization problem by Nibale, Fitzum, and Paolo, which is a much more efficient way to generate tests than whole test with generation. And it does this by adapting a generic genetic search algorithm to the specifics of the search problem we're facing. And you can only do this if you truly understand what is happening in that black box. Okay, so the other point I want to talk about is the second problem in here, which is the actual test oracles, the expressiveness of the assertions we're generating. I showed some diagrams from 2010 where we evaluated MuTest on a couple of libraries, comparing artificially seeded defects, mutants. Since 2010 and the time until now, it's become very popular to evaluate your tools on benchmarks of bugs, such as defects for J. And we did this using different configurations of EvoSuite at the time. I suppose most of you will know defects for J. It's a collection of 357 real bugs, including the libraries we used in the original MuTest study. And what you can see is that for some of the faults, the success rate is quite decent, but for many, it's actually not. And only to a certain degree can we attribute this to problems with test generation. And of course, there are problems with test generation. Half of the test suites did not manage to fully cover the buggy code in this bug database. And then a large share of the test suite did not even manage to partially cover the bug, didn't even get close to touching any of the lines that were modified as part of the bug fix. But there's another problem in here that prevents automatically generated tests from finding these defects, and that's the test oracles. So we look closer at the bugs that were found out of this, out of the 357 real bugs. For example, we saw that 147 were found using assertions, 109 using exceptions, and 56 using both out of the 357. So this is for found in any of the executions, they're not consistently found. So the number of bugs found with assertions is actually substantially higher. And to put this into perspective, we compared this with the number of assertions we would need in order to find the fault. So we looked at the developer-written test cases and determined whether the developer-written test cases, and defects for today, these are regression tests written by developers in response to the bugs. And in order to find these bugs, assertions are very common, and not only exceptions. And the automated test generator struggles much more in finding bugs that require you to formulate an assertion than it does in finding bugs that can be found simply by triggering an exception. So there is a substantial problem there, which is coming up with the right test oracles. And so here's the second paper I wanted to point out. And that is Test Oracle Assessment and Improvement, which is based on Gunnell's PhD thesis. And again, it's by Paolo and David Clark and Mark Harmon. So this paper uses similar techniques to MuTest, And in my opinion, it's the most fascinating follow-up work on the Oracle problem to date. So very badly and briefly summarized, what happens in this paper is they look at the assertions and tests and try and improve them by removing false positives and false negatives. To remove a false positive, what you have to do is search for a test input that leads to an assertion violation. And the search is exactly the same kind of idea as behind, for example, MuTest. And to remove false negatives, what they do is they use mutants that are supposed to be detected, but are not by the assertions. Okay, so these are the two papers that I wanted to point out. I'm going to hand over to Andreas in a second to summarize my part of the presentation. I suppose there's two conclusions here. Conclusion one, Paolo's papers are really great. And conclusion two, the test generation and Oracle problem are not solved problems, but in order to make progress, I think understanding the black boxes we use is super important. Okay, thank you very much. Andreas, over to you.
One, two. Oh, so sorry. Oops. So let me see whether everything works. Here we go, sharing the screen. I hope you can hear me all right. Wonderful. Yes. So let's continue. So as Gordon pointed out already in his part of the talk, we are working on problems that have been around for quite some time and that also will be around for quite some time. Again, the Oracle problem, knowing when a test fails, the mutation problem, how to come up with changes to the code that actually feel like real bugs, and of course the everlasting problem of test generation. And the very unique contribution maybe of our 2010 paper was that actually by bringing together these three problems, we created a solution out of that. So each problem by itself is very hard to solve, but by bringing in more problems, we would eventually be able to create a solution. And that's still something I very much like today about this. And working with Gordon on this was so much fun. I very look fondly back on these days. What Gordon has not told you, of course, is also the immense amount of work that this was, because, well, we had to build these and when I say we, it is a paper by Fraser and Zeller. I would like to very much point that out, because we also had to build these things, not like we had plenty of infrastructures available at the time. And you also need to understand that even as much as you do on all these problems, each of these problems has fundamental limitations that all go back to the undecidability problem. So when you work on any of these, it's a bit like Sisyphus. You push the problem a bit further, and you push it further, and you push it up the hill. But well, you know deep in your heart you will never be able to make it, which is in some way great for science because, well, there will always be new generations of scientists working on that. But still, why are we doing this? And I am pretty old these days, but I'm not as old, but I'm not old enough to remember John F. Kennedy saying his famous phrase, why do we choose to go to the moon? And he said it in his very famous speech, we choose to go to the moon in this decade and to the other things, not because they're easy, but because they're hard. And we want to do the hard things. We don't want to do the easy things. This is what fuels us as a scientist. And I am actually old enough to remember the moon landing. So I was 3.5 years old at the time. So that was about it. And of course, well, comparing what we did here, what we did to the moon landing, well, this is rocket science, right? This is them. And in comparison, well, we went as far as climbing on a small piece of wood. having some beer, that was great too. But there are differences in the achievements. We may have gone further than others, and we have made some dent in the universe. But there are folks which have been going much farther than we went. But still, we work on these things, and we assume because there is some mythical place where we will finally emerge at the top of the mountain and find solace. For us, this is the correctness of software. Everything we do is to get there, out of the fog into the light, and anything that helps with that will be fine and will contribute towards this mythical goal. I do, unfortunately, not always see such a devotion towards a great goal in today's papers, or to be precise, in today's paper submissions. I'm frequently working as a reviewer, and I think that things have changed a bit. I brought along some examples of paper titles that I get to see these days, and none of these titles is real. I've changed them to protect the innocent. Just to give you a few examples here. Enhancing grep with a -- help regex option. I'm seeing papers that feel exactly like this, taking some arbitrary pull request and making a paper out of it. Or where should users send bug reports to an empirical study? Should they send it to the official bug reports address or maybe somewhere else? And when will they be looked at? You can certainly do a study on that. Does unreachable code have bugs? That's actually a very interesting philosophical question. If you cannot execute code, there will be no failure, and by definition, can there be a bug? Might be worth investigating. Or an improved package manager for C64 Basic. C64, this is a Commodore 64 computer which was popular in the mid-80s, if I recall it right. And the fun part about these papers is when we as reviewers are supposed to grade them. Look, let's take this one, for instance. They're novel. This option did not exist before, and therefore it's new. Papers are excellently written. Every year I see better and better written papers. It's amazing. It's also, there's an evaluation which is super sound. Yes, people who have trouble with regex can actually find that such an option could help them. It's also super reproducible. But then the last point is the significance. What do these things change? Why should I care? That's what I ask myself. Why do people research such things? And why is this research actually there? Is this actually research? And this has changed my attitude over time. So in 2010, when I was a reviewer, in my pile of papers, it used to be the case that half of these papers would get accepted, either by me pushing for them or by them being good papers in the first place. I had a far above average set of accepted papers. And yes, if I liked a paper, I would very much fight for it. Of course, there would also be 50% reject, but there we go. Today, this is actually different. Today, I just checked my personal recent numbers. My acceptance rate has gone down to 10%. And which does not mean that 10% of the papers that I get, I vote for acceptance, but 10% of these eventually end up in the program. So I'm actually lower than average at this point. And this is, well, for some, the most important reason is still unsoundness, that's right. But there's also plenty of papers which are not significant enough to actually fight for them. And this makes me, well, I am a reviewer too here. I'm becoming more and more of a bad guy. And I'm wondering, is it okay to reject papers that are well done on every aspect, but which likely nobody will read or care about? Is it okay if we as a community will be are seen as relevant or irrelevant? I mean, I'll be co-chair of ISSTA in 2 years, so please help me not turning into a universal rejecter. This might be pretty bad for our community. I'm happy to get advice by the community here. But what I also would love to say is that we, in particular, we here as the ISSTA community, we should continue to tackle the hard problems: test generation, oracles, mutations, analysis, proofs, processes, anything that helps us getting out of the fog and a bit further towards the light. And it may not come as a surprise that it's precisely this conference where I have always felt at ease and at a community that is oriented towards that goal, which is actually why 10 years ago, we submitted our paper to ISSTA and to no other conference, because this is our conference, this is our community, and we wish it long life and prosper. And with that, we'd like to close. Thank you very much for the award. A big thanks to the selection committee for their hard work. Thanks to you all for listening. And I guess we're happy to take questions, right? Thank you very much.
Thank you very much for the nice talk. I'll give you the applause from the whole audience. And congratulations again for the award. Very well deserved and very impressive. So I shall check for questions. So we are still waiting for questions on Slack. So for the audience, please place your questions on the date 30900 Keynote channel. And I will start with some questions, and let's see if the audience will also place some. So for Gordon, I had some technical questions. So you mentioned the oracle problem, that it is hard, and I was just curious if you guys did also work on the oracle problem involving reference types or data structures, or no?
Well, if we're generating tests for Java, then by definition, we're creating references of complex objects. But this is still one of the main challenges in generating valid configurations of these. That's
Okay.
Typically in my diagram, the bottom left corner where there's a big circle of classes we can't cover at all. They tend to be complex objects we can't instantiate.
Okay, so that is an area where the students in the audience maybe should take a look. I have also done a lot of work on that one, and yeah, it seems it's still not a solved problem. So this goes back to Andreas' presentation, that it seems is like a Sisyphus work, and keep doing it, keep doing what we are doing. So is there something fundamental that we should change? People proposed before, maybe other languages that are safer, synthesis, or maybe we should not keep doing what we are doing if we cannot solve it, or I mean, I'm happy to do it, but philosophically, we really want to have programs safe, not to have cool new research topics. So can we ever solve the problem?
One thing, and this is pretty practical advice, I wish I had learned earlier, is that building an infrastructure in Java takes an awful amount of work. And I have had a student, for instance, who has been working on a topic that is extremely popular in my group these days. This is about mining grammars, meaning that we want to learn what the input format of a program is. And he did this in Java from the very beginning. And this was with dynamic tracking of input characters throughout the program. And he found 500 million bugs in the Java interpreter with this way, which is great, but he had also to work around each and every of these bugs. And then after it worked for the first time, then we found out, well, this doesn't really work. We have to come up with another algorithm. And then we changed the algorithm, which actually meant that we had to redo most parts of the implementation. And then we found a huge set of other bugs. And what we do today, and this is very different, is we do lots of prototyping in Python, notably with Jupyter notebooks. And the work that some of my students have spent months on is something that I can do in one afternoon in a Python prototype. Of course, this prototype will not be nearly as efficient or nearly as powerful as what my students can build. And I would love to point out that I'm a much better programmer than my students, but that's not the case at all. It's just this prototyping effect that we can focus on the algorithms and get the algorithms right in the first place before we go and build something for a more industry-like language like Java or C. And that's something I wish I had learned before. That is actually applying software engineering mechanisms, being agile, building prototypes first, getting the algorithms right first, and only then start with the big infrastructures.
Thank you. Gordon, would you like to add anything?
Well, I mean, I fully agree with everything. If you look at Evo Suite, then probably 90-something% of the code is working around specifically the things that Andreas pointed out. And the complexity of the search algorithm is nothing compared to all this effort. So wholeheartedly agree with Andreas here.
Okay, thank you. So we have a question on Slack from Rahul Gopinath. From the perspective of test generation, what do you think of fuzzing research today?
Gordon, you want to come first?
Okay, well, I think there's great things happening here. One thing maybe to point out though is that one of the diagrams I had was the number of bugs that you can find with an exception and the program crashing, and the number of cases where you need to have a test oracle that somehow captures the intended functionality in order to find the bug. And then that's a problem that fuzzing doesn't address, right? It addresses crashing the program, finding ways to find an overflow and so on, but it kind of sidesteps the oracle problem. But other than that, of course, there's very cool things happening there. And Andreas, of course, is the expert on this.
Actually, I'm also looking at the fuzzing research in awe because there's lots and lots happening there. What I find very interesting is that lots of fuzzing is, of course, being done by security researchers, and if you ever thought that software engineering was very focused on actually getting things done and to scale and making things useful, this is even far more so in the security community. Usefulness counts, bugs count, the way vulnerabilities count. The way you get them doesn't matter. Whether this is replicable, whether this has any abstraction to it, doesn't matter. If you come out victorious, if you build something and come out victorious after letting this run for a day with a couple of new CVEs, you are the king. And this is from the standpoint of somebody who comes more from more traditional test generation perspective, this is both amazing because people simply solve problems one after the other. But it's also a bit sad because many of these problems are being solved in a very ad hoc way. Also simply in order to satisfy some benchmarks which are pretty questionable. And I would sometimes wish that we could join forces here, bringing together the usefulness or the usefulness-centric perspective of the security community with a somewhat more, say, teaching-oriented and abstraction-oriented means as software engineers do. Because in the end, in the security domain, you end up with a huge set of implementations of fuzzers, but you don't know why they work, you don't know how they work. The fact that you don't know how they work also opens up the door for very interesting ways of teaching, of cheating, meaning that you over-optimize towards a benchmark. And I think it's also a big research opportunity for us as a more traditional software testing and analysis community to find out, to carve out the essential algorithms such that they can be taught, such that they can be reused, such that they can be modularized, and also, on the other hand, also maybe teach the security community a bit about the value of abstractions, that here are things that actually here's an algorithm, and this algorithm is made to last, and it's not just one more tool that is hacked together, but here is the core of an approach, and this is what we want to do as scientists, doing approaches that actually last over time.
Okay, thank you. And actually, there is another question that is related to your response. So Jose Miguel Rojas comments, the nicest part of your MuTest approach is that its heuristics are understandable and explainable. And then he says ML, I suppose machine learning, seems to be becoming trendy in this field, but do you think it has any future in producing meaningful assertions? Who would like to respond?
So it depends what type of ML you mean. I think we're in a phase where it's super popular to try out lots of black boxes because they can solve things we haven't been able to do previously. I think sooner or later we're going to face the question of explainable models there as well. So sooner or later, yes, I think there is a future for that.
I suppose his question is about using ML for inferring assertions, maybe, but the other side of the question could be how do you see applying your techniques to ML also? This could also come from me. So would you like to comment on that?
Well, it's actually a very nice idea to use that on machine learning models. Thank you very much for that idea.
I think the Oracle problem will be pretty hard in that domain.
Yes, absolutely.
I would like to add, I see a big potential in applying machine learning in conjunction and towards test generation and also assertion generation. See, if you look at code, you have tree structures, there you go. If you look at inputs or data structures for that matter, you're gonna have structural inputs, and for both of these, and for both data that goes into functions as well as for code, the structure is well known. And if you have sufficiently many examples to learn from, you may be able to learn that particular aspects of coding are best done in a particular way, which is what generative neural networks, for instance, might well be able to produce. And if on top of that, you have some test generator that actually is able to validate what a generative network does and provide feedback to it, whether this is in line with whether this is actually executable or whether this actually is meaningful, also in a static way. There are many ways that large bodies of code on one side, large amounts of execution as produced by test generators can be combined with machine learning techniques to actually produce mutations, to produce assertions, to produce repairs. And this is maybe one of the most exciting fields or most exciting possible applications of machine learning in the next years.
Thank you. So Jose, I think, agrees also with the interpretation of his question. So we have just 1 minute left, and I wanted to ask a question about the reviewing and papers. So the more controversial part of your talk, Andreas. So it's more of a joke, but how were the reviews for your 2010 paper? Were they stellar or were they borderline?
Actually, we dug these out. We dug these out, Gordon. Am I correct? Yes. And they were so and so, I would say, above the bar. Yes, people said this is new, and people haven't, and this hasn't been tried before, but certainly not award-winning. Definitely not. This is actually something I see, and this is actually constant. Something that is. This is actually true for all of the papers for which I got Test of Time awards. None of them got great reviews in the first place, and some of them actually got rejected because you come up with something that is out of the ordinary, that is precisely not incremental, that is not just bolting another option to an existing tool, but that comes out of the blue and brings together things that haven't been brought together before. And then you need reviewers who are experts in all of these fields. I mean, we also had to become experts in these fields too. And so what you end up with reviews that are careful, where people do not champion your paper right away, but where people give you the benefit of the doubt. But I think that all of the reviewers agreed on there is some potential in there, and then they let it in.
Okay, sounds good. So this is also good encouragement for students and authors. Don't give up, even if your paper is rejected. It could get into another conference and win Best Paper Award in 10 years. So,
if you have tenure, then that is.
Okay, yeah. You should secure tenure in the meantime. So I think we are out of time. Thank you again for the very nice presentation, and please follow Slack in case people ask more questions. And